Okay, guys, I think we can start today's session. Yesterday's session, if you attended, you may have an idea like we have started with SLAM algorithms that is using in robotics. So, the intention of this chapter is to like explore different SLAM algorithms like 2D SLAM, 3D SLAM, then visual SLAM. Uh, different types of slam algorithm. Like we are not configuring all the slam algorithm. For some slam algorithm we will be seeing like how to uh, configure, and for some slams we will see what are the inputs that we have to give, and what is the expected output, and maybe some videos, some demonstrations. So and also we can discuss like what are the sensors that we can use for creating this map, and some kind of sensor fusion. What are the different sensors that is using for fusing the data for making a map. Okay. So yesterday, I think we have started with the basics, like what is objective of these SLAM algorithms. SLAM stands for simultaneous localization and mapping, and I think we started and reached up to the G mapping. Yeah. So, but I didn't explain about G mapping. I was just talking about um, some papers like Fast Slam, which was one of the oldest paper in Slam, and this G mapping is actually based on that Fast Slam. Okay. So regarding the number of packages available in ROS related to SLAM and all, there are many packages actually available. Okay, there are many packages available. So we can categorize the SLAM as 2D SLAM. 2D SLAM means it's basically creating the map of the environment in a 2D map. Okay, and 3D SLAM, it's basically creating the 3D point cloud. um, and visual slam, it's actually also considering the camera, so we will get the realistic 3D point cloud. Okay, realistic in the sense like it's not like, maybe I can show you the 3D map using 3D map using Velodyne. So it doesn't have any features in the sense the camera features. I mean, it's only the lidar, right? So this is one of the image that you can check, like the 3D mapping using the Velodyne. Okay, and if you check for the visual slam, you can find it's mainly working on the camera and its features. Okay, so there are multiple combination, like we can use cameras and Velodyne, and then it can fuse together and we will get the realistic map of the environment. Okay, so there are multiple combinations. So literally, like we can say like 2D slam, 3D slam, and visual slam. Okay. um, yeah. Then I think there are multiple categories, but we are only focusing on these slam algorithm. So we can start with the 2D slam. Okay, so basically the 2D slam, uh, the input will be the laser scan, then the odometry, then the IMU. The output will be the 2D map. So maybe I can start with an example, and then I will be like coming back to the 2D slam again. Okay, so I think everything can be explained very easily using an example. So that's why I'm starting with the example. You may have seen this, but yeah, this is a different context. So what I'm first trying to do is I'm starting a simulation of turtle board. So let me start the turtle board simulation, and the objective of this task is that we have to map the turtlebot environment. That is what we are planning to do. Okay, so the simulation is ready. Okay, I think you already have seen this simulation before. So our objective is to map this environment, this environment, and we are planning to map it. So first we are trying with a 2D SLAM technique. Okay, so there are a bunch of 2D SLAM algorithm implementation available in ROS. So the turtlebot packages are simply configured with that node, and we can simply call it. Okay, I think some SLAM will work. I didn't tested everything, but let me check the first one. Okay, so you will get a clarity, I will say. Okay, we have okay, let me just turtlebot SLAM. Rather than that, let me check if there is any. Okay, I think SLAM will be fine. SLAM. Okay, turtlebot SLAM G mapping. So we are running the SLAM algorithm, and then I am actually taking the visualization in ROS in order to see the see how the G mapping works. So turtlebot visualization, let me check. Navigation, or yeah, maybe I think I can take the ROS, plain ROS. And I'm just simply including the robot model, and also the map. I need to run an extra node, I guess. Let me check. Turtlebot 3, I think it's in the bring up. So when you run the simulation, I think we have to run the remote, I guess. ROS launch, turtlebot 3 bring up, then turtlebot 3 remote. Yeah, the remote. Okay, it's actually starting the TF and all, so that is actually there. So we have to start the simulation and the turtlebot 3 remote. Then you can see the SLAM started working, and you can see the robot here. Okay, and you can see the laser scan here. Maybe I can just increase the size. Okay, and I can also add the odometry. Okay, so now what I'm doing is, so currently the SLAM algorithm, SLAM G mapping, the fast SLAM is active, and in order to work with the SLAM, what you have to do is, I mentioned that SLAM is mapping and localization, meaning you can move the robot manually, and it can map the environment, or you can load with some exploratory algorithm. Then the robot will be like exploring and keep on mapping. So now what I'm trying to do is, I am just steering the robot. I'm just driving the robot using RQT plugin called robot steering. So I'm just giving some forward motion, so you can able to see the the robot is moving and it's keep on building the map. Okay, so that is one thing that SLAM algorithm does. And also, if you check the robot position, okay, if you check the robot position, just check with respect to the map. Yeah, so there is a question from Rohan. So what is covariance? It's actually the noise, I will say. I mean, there are, I mean, if you visualize the covariance, it will be like this. So there is an additional entry in the odometry topic. So if you just check the odom ROS message, in the odometry message, you can find there is a covariance, pose with covariance, and here it is the covariance. So I think it's related to noise or something. I need to check exactly. It seems like it's a raw matrix. I mean, yeah, it's a 6 by 6 covariance matrix. It seems we can actually manually give it. From my understanding, I think it's giving some noise value or something that I can check it. Okay, I'm not very sure, but I was actually using it, some dummy values in the covariance. Yeah, I think so. It may be related to the probability something. I need to confirm. Yeah. So anyway, the odometry is an estimate, right? So it can be related to some probability values, probability terms. Yeah. So we are actually using covariance metrics in multiple occasion. I think one is the odometry, and yeah, in some other occasion I'm not remembering it. It's actually some useful I mean factor, but I need to double check. Okay, so so here you can find the robot position is here, right? And when you check it in the simulation, it's also here. So that means if you compare the robot position in the world, and if you compare the robot position with respect to the map, it's actually the same. It's actually the same. That means the robot is actually mapping and also it's localizing. Okay, it's actually creating the map of the environment by taking account of the obstacle. So the main input here is the laser scan that you can see, and also the wheel encoders. We will get back to that anyway. This is just a demonstration. So when the robot moves to move through these obstacles, it is getting the complete clarity of the environment. So basically, uh, for a robot or for a human being, what we are really looking into is the obstacles, right? Obstacles, like if we want to navigate to a terrain, we are basically looking for the obstacles, right? If there is obstacle, we have to avoid it. Okay, so um, these obstacle profile also help humans to create an internal map in our mind. I mean, imagine uh, imagine a desert, okay? A desert without having anything, okay? So it's very difficult to map the desert, right? It's very, I mean, it's plain. It is not having anything. But if it is an environment with a lot of stuff, then you can memorize the things, right, based on the features. So that concept, maybe I think we can apply for robots as well, in the SLAM algorithm context. Like if there are obstacles, the um, the robot can detect that using the range sensors or the laser scans, and then that detection and that features can be used in the SLAM algorithm, um, and we can create the map, something like that. So there is a question from Kalpesh, sir, how is the map represent as data meaning in the code? Yeah, so I will get back to that, Kalpesh. So this is just a demonstration. So we will be seeing how we can hold the map, what is the representation and all we can see. Okay, so this is just a representation. I'm not explaining at all. Okay, just want to see how the SLAM works. Okay, and you can see it's basically um, uh, it's basically accounting the obstacles. Okay, yeah, there is a question from Tejas, how do we know if it is in mapping mode or localization mode? So actually Tejas, SLAM is actually doing both at the same time. So it's there is no mode actually. I mean, uh, at- in the same time it can do the mapping and localization. Okay, so that's how it is working. Otherwise, imagine like the robot is mapping and it can't able to find the location with respect to the map, then the mapping will not be good. So I mean, for the mapping, the localization is also required. I mean, the robot pose is actually required. With the respect to the robot pose only, it is mapping. For example, uh, the robot, imagine you have a robot and you are putting the robot in a stand. Okay, so when you drive the robot, only the wheels will rotate but it's not moving in the ground. So what happening is that the pose internally, the pose will get updated, but the obstacles is not changing. So the map will not, I mean, will not be created. The proper map will not be created. So yeah, so there is a question from Tejas. Yeah, simultaneous, but I mean to say, if we give a 2D pose goal, that time map is already present and robot is localized, right? So Tejas, I think for the 2D pose goal and all, we need to run the move base as well. So we have talked about the navigation stack, right? So these SLAM algorithm can give us the location of the robot, current location, and it can also do the mapping. Using that location, the move base can able to command the robot from A to B. Okay, so that is one thing, like we can run G mapping, and you can run the move base to move the robot from A to B. Otherwise, we can save this map and we can run a localization algorithm. So there will not be any mapping happening. So that is the AMCL. Okay. So so the rest of the question is basically we need to map the environment at least once. Yeah. So that's what I meant. Like we can do in multiple ways. In order to navigate from A to B, you can use a SLAM algorithm with the navigation stack, or we can simply map the environment, save it as a image file, and then we can use that image file along with a localization algorithm like AMCL, and you can localize the robot on the map, and you can deploy the navigation stack to go from A to B. So this is what we are commonly doing. Okay, in the second method it's also SLAM only, right? No, I mean the second method. Do you mean the AMCL with the saved map? No, no. Yeah, saving the map first, then AMCL. Yes. So actually, when you do the SLAM, mostly I mean, we are thinking that it is mainly for the mapping, right? It's mainly for that is what the regular procedure that we are doing to create a map. Just run the SLAM algorithm, create the map, save it, and then we are running the localization. But we can also do in another way, like without the AMCL, we can run the G mapping. Okay, we can run the SLAM. So what will happen is that it will uh, it will keep on mapping it. So that's how the exploratory algorithms work. Maybe I can show you a video so you will get an understanding. So if you take explorite ROS, I'm not sure you have seen this package or not. it's mainly for autonomous exploration and mapping. So I can show you a video. Okay. Uh, so here is a video. It's a Turtleboat 2 robot, and what happening is that the robot is simply exploring and creating the map. Okay, we are not manually controlling it. So how is this happening? So this is actually the combination of three techniques. One is obviously SLAM. So using SLAM, it is creating the map. Second is the navigation stack, because we can only move the robot from A to B with the help of navigation stack. I mean, we can use some other methods, but basically we can use the navigation stack easily to move the robot from A to B. Is that enough? No, right? The robot is autonomously moving, randomly moving the environment, and it is mapping all the room, right? So there is an exploratory algorithm as well. So the exploratory algorithm works like it needs SLAM algorithm. So what happening is that these are the three units I mentioned. So the explore light algorithm will be keep on subscribing the map updates from SLAM algorithm. Mainly it is preferring G mapping. Okay. So, and based on that, based on the generated map, it is actually putting some random goals on the map. Okay, with the help of MoveBase. Okay, so instead of manual control, the exploratory algorithm can find the area that it can traverse. Okay, so these things are basically doing by the explorate algorithm. So we can do this combination mainly for the exploration application. Okay, I'm just sending I'm just sharing the link so you can have a look. Okay. So this is merely for the exploration, because exploration is actually finding the unknown areas, right? So that is the same concept that we are applied in the subterranean challenge. In the subterranean challenge, what we had was some unknown area like caves and all. So we actually deploying the robot with these three algorithms. SLAM for mapping, and it can also localize, then exploring algorithm, and then the navigation stack. I mean, it may be different nodes, but three components will be there in that kind of. So there is a question from Tejas. So does it avoid dynamic obstacle while exploration? Yes, it does, because it is using the navigation stack, right? So navigation stack is actually taking care of dynamic obstacle. Okay, so that's what. And also the SLAM can also map the dynamic obstacle on the map. So in the combination of all these things, we can avoid the obstacles. Okay. So this is the this is the demo, and these are the two methods that we can use for exploration and also navigation. I mean pure navigation, A to B. So for exploration, we can use an exploration algorithm with G mapping and navigation stack. For pure navigation, like going from A to B, you can use localization algorithm along with the saved map. So maybe I can also show that, and then I can come back to the G mapping. So I'm starting the world. I think I have shown that, but this is a different context. So let me start the localization. So there is a package called Turtleboat 3 navigation, I guess. Yeah, and Turtleboat 3 navigation. Yes, it's starting. Yes, so this is the localization mode. So what we are doing now is, currently you can check the pose of the robot. It's in the center, right? It's in the center. So the pose of the robot that is currently showing is actually false. It's not true. So this is actually the work of the localization node. Okay, using AMCL is one of the example for the localization algorithm, but AMCL is actually initialized with 0 now. Okay, so AMCL need an initial estimate of the pose. So I'm just giving an initial estimate here. So in the real world, or sorry, in the simulated world, the robot pose is a real robot is placing here. So we are giving an initial pose of the robot here. Okay, so it is matching with the laser scan. So you can find it is correct, right? The pose of the robot is correct. So you can find a lot of I mean particles around it. It's called the particle filters or AMCL particles. Okay, more the particles means less the accuracy. Okay, so currently three things are running. Not three. Yeah, two things. One is the navigation stack. Second is the localization algorithm called AMCL, and this is a saved map. Okay, so once you give the goal position, it is not creating the map actually. It is finding the current pose of the robot. The AMCL responsibility is to find the robot pose. So when you move the robot, you can find the particles are disappearing, means it is getting the good estimate of the robot position, and then it can able to do the path planning from A to B. So this is the AMCL part. Okay, so I just want to clarify the difference between AMCL and SLAM. So AMCL is only doing localization, SLAM is doing both. Okay, so coming back to the G mapping, which is one of the popular SLAM algorithms available, which is actually the wrapper. This package is actually the wrapper of OpenSlam.org. Okay, I think I have shared that link yesterday. Maybe I can share today as well. So if you just check the G mapping package on ROS wiki, you can find some interesting stuff. Like the G mapping is actually a single node. It's a ROS node. Okay, and if you just go to the nodes, this one, okay, you can find what are the topics it is subscribing, what are the topics it is publishing. Okay, that is what a node does, right? It may publish some topics, it may call some service, it may host some service. I mean, the regular stuff that a node can does, right? So for SLAM G mapping, so there is a package called SLAM G mapping. Okay, SLAM G mapping. Inside that there is another package called G mapping. So inside this G mapping only there is a node called SLAM G mapping. Okay, so basically there is a node which can subscribe to the TF information of the robot, then the scan, laser scan of the robot. Okay, so from the TF, the node will get the information about the transformation of the robot, like where is the base link, where is the laser scan link, what is the odometry. Odometry transformation is also in the TF. Okay, so for working with this node, the first thing is that we have to make sure the TF is proper. Okay, TF is proper. TF is proper in the sense we have to publish the TF at least from odometry to base footprint, base link, then the links, other links. Okay, so maybe I can show you, like when you start the simulation, turtleworld.launch, we can simply check the TF first. Okay, TF. So that is actually simply launching the simulation. Okay, it's not starting any other, I mean, it's not starting the URDF properly. So maybe you have to run these thing like turtleboard 3 bring up, turtleboard 3 remote, this only publishing the TF. Okay, so if you just check the RQT GUI, oh, not RQT graph, not RQT graph, just a second. Yeah, RQT. Okay, so I'm simply loading the TF tree, and then you can find the TF tree. So this is the TF tree that we want for working with the G mapping. Okay, so what happening is that in a simulation, the ODOM to base footprint can be published from the differential drive plugin in Gazebo, and the base footprint to base link and everything is already in the URDF. Okay, so the ODOM to base footprint is what we have to provide if you have a real robot. So if you if you want to create a real robot, you have to calculate the ODOM and you have to publish this transformation. Okay, ODOM to base footprint. For example, when you start the robot, ODOM will be 0, right? And when you move the robot, the ODOM will be like moving in X, incrementing in X direction or Y direction. So that thing has to add here. Okay, that increment will be adding to this. So from the 0th position, where is the base footprint of the robot now? Maybe the translation may be 1 meter and rotation may be like some radians or something. So you have to create this TF structure, then only you can start working on the G mapping. Okay, so TF is very important. And the next is the scan data. So I think you have seen in the Turtleboard simulation, there is a LiDAR on the top of the Turtleboard. So that is actually providing the scan data. So you can able to see the LiDAR, right? So in order to visualize, just take the RVs and then just make the, so currently the fixed frame is ODOM, there is no map, and we have to add the laser scan. Okay, let me check. So you can find the laser scan is here. Okay, and we can add the robot model. So the robot model is here. Okay, so you can see the laser scan with respect to the robot's center. Okay, so these two are the inputs to the SLAM algorithm. Okay, subscribing means it is taking inside the node. Okay, and what is it outputting? What is it actually giving to us? It is actually publishing a topic called map. Okay, map. It's a type called occupancy grid. Okay, it's mainly for for holding a map data. So like you can find map is basically an image. Okay, we can save it as an image. So in the occupancy grid message, you can find the there is a header and there is a metadata. So like this is a map, right? So a map is like it's a file in the sense it is having length and breadth, resolution, all this stuff. You have visualized that, right? When the robot is moving, the map is building. So these parameters are holding inside this map metadata, and this data is having this data that's an array which is holding the values of each pixels. So each pixel can be like either the some of the map pose can be occupied or it may be empty. Okay, so those kind of data is actually holding inside this array. Okay, so this is what the gmapping is publishing the metadata and also the map. Okay, so yeah, and also there are tons of parameters with the gmapping node. So what happening is that these kind of nodes are very easy to, I mean, not, I will not say easy in the sense like this node is the implementation of FastLAM. Okay, and for the FastLAM there are many parameters in the algorithm. Okay, there are many parameters, and all these parameters are exposed as ROS parameters. So what you can do is you can simply start this node with all these parameters and you can fine tune it. Okay, so if you if you take any SLAM algorithm in ROS, they have implemented in a such a way that this is like a template. This is a skeleton. This node is actually skeleton, and this skeleton is filled with all this flesh in the form of parameters. Okay, so if you provide the proper parameters to this node, then only the algorithms will work properly. I think you got an idea, right? So the parameters are the important one of the important factor in each SLAM algorithm, because if there is any parameters I mean it's not matching, or the mapping and localization can affect. Okay, I'm not I don't know all the parameters. There is a description in each parameter, so whenever it required we will be like doing some fine tuning. Okay, so the fine tuning of these parameters is very important. Okay, so now I'm planning to show you how to start this node. So it's nothing complicated. There is a node called SLAM gmapping. We are just starting the node and we are just passing these parameters. That's it. Okay, so the reference that I'm giving you is the Turtleboard SLAM. Yeah, Turtleboard SLAM, Turtleboard 3 SLAM. So that is a package that I am giving as a reference. Let me check. There is a repository. Yeah, Turtleboard workspace, and if you just check, there is a SLAM package. So this is actually the reference that I want to give to you, because this SLAM algorithm, I mean this SLAM package having set of SLAM algorithm configuration. Okay, for example, if you just go to the launch file, you can find the launch file for gmapping, so which is basically like starting this node. Okay, maybe I can just show you. So this is how we can start the gmapping SLAM algorithm. Okay, so simply starting the node. Okay, it's in the package called gmapping. The node executable name is SLAM gmapping, and then you can name the node like Turtleboard 3 SLAM gmapping or something. And then what we are doing is we are feeding the nodes with the parameters. So these are some basic parameter. What is the base frame? What is the ODOM frame? What is the map frame? And after that, what we are doing is we are loading a set of parameters as a YAML file. Okay, so this is how we can load the parameters as a YAML file, in a YAML file. So just use this command ROS param load and just give the parameters in an additional file. Okay, you can also put these parameters inside the param tag, but the problem is there are tons of parameters, actually like 10 to 20 parameters. So what they did was they just put all these parameters inside the config folder. Okay, so this is the YAML file and these all are the parameters. Okay, so you can change these parameters and start the node. So yeah, so there is a question, how is this ROS parameter called inside the code? How is this ROS parameter called in? Yeah, so maybe I can show you that. So these parameters are get passed to the nodes, right? So the question is like how the nodes are receiving these parameters. So it's very simple. Like these nodes, I mean these parameters now, we are calling these parameters as private parameters. Private, because if you write a parameters outside the node, it's a public parameter. We can actually set the privacy of the parameters in ROS parameter. So these all are exclusive for the gmapping node. Okay, gmapping node, I mean slam gmapping is only using it. And if you check the code, you can see it is simply using C++ param function to read it. So for example, I can simply show you the node of gmapping. So slam gmapping.cpp, and you can find these lines, right? So it's actually retrieving all the private parameters using this. So we have a map frame, auto frame, and all these parameters. There is a tons of parameters it is exposing. So when the gmapping node is started, when it's starting, the init function, I mean it's a custom function, but I think it may be calling inside maybe inside the constructor or something. Yeah, in the constructor. Okay, so inside the this is not the constructor, but inside the constructor it is calling the init function. Okay, so inside the init function it is loading, I mean doing a lot of stuff. It is starting the some libraries, and first step is the like retrieving all the parameters. Then only this algorithm can work. Okay, yes. So yeah, so this is how we can start the gmapping. So like that, they have exposed multiple SLAM algorithms. One is the gmapping, one is the Hector SLAM, then Kato SLAM, then Frontier. Yeah, this is for the exploration, and there is a cartographer. Okay, so they actually made everything simple. They have a launch file called turtleboard3 slam, and inside that you can actually give the I mean what is the slam algorithm that you are going to use. Okay, so let me just, yeah, so you can see here based on the slam method argument, okay, you can simply swap from different slam algorithm. If you by default it is gmapping, but if you set the slam methods as cartographer, the cartographer will work. I mean cartographer node will be running, then Hector, Kato, then this is for the exploration. Okay, so whenever we set the slam method argument, if it is gmapping, it will start the desired launch file. Okay, it will launch like turtleboard slam launch turtleboard3 underscore gmapping. So that is the launch file name. Then turtleboard3 underscore Hector, turtleboard3 underscore Kato, something like that. So make sure you have installed the cartographer. Maybe we can have a try, so you will get a clarity. So we are starting the simulation. Oh, just a second. And we are starting the TF, and we are starting the yeah, slam, right? We have to start the slam. So this was the launch file. Wait, turtleboard3 slam. Then if you double tap, you can find slam method, which is a command line argument for this launch file, and you can give any slam algorithm that you like. So if that is already installed on your system, it will start working. Okay, let me try with cartographer. I'm not sure that is installed. So cartographer, so it will start loading the cartographer launch file. So you can find yeah, so it's not able to find the cartographer ROS package. What we can do is we can maybe install it. Okay, try to install it and then check whether it is working or not. So I'm simply installing ROS cartographer. Now we take cartographer. Oh, I think the cartographer package, not sure it is available or not. Maybe I can do a search. Yes. Cartographer. So this is another SLAM algorithm implementation done by Google. They actually started it. Seems like the cartographer package is not available. Maybe we have to install it manually by source code. Maybe we have to install, so we can't able to demonstrate. Maybe we can try Carto, which is again another algorithm. So yeah, so there are some SLAM Carto available. Okay, so we can simply install these packages in order to test the Carto SLAM. Again, I didn't tested that, but let me try. So just install the required SLAM package. So I just want to like demonstrate this launch file working. Okay, so the G mapping we tested, that is working, and there are Hector SLAM, Carto SLAMs available. So what I'm simply doing is that I'm simply installing the SLAM that is already available. So and we can try whether we can start it from the launch file. Okay, and also I just want to install Hector SLAM. So let's see that work. Just a second. Yes. Okay, it seems like it's finishing. Yeah, it will take some time because we are running the simulation as well, so it will take yeah. Maybe we can just close the simulation to allocate some more CPU into it. Yeah, I think it's completed, and we can also search for Hector, which is another SLAM algorithm. Yeah, I think Hector SLAM, I'm not sure it's installed or not. Let's see. Yeah, we need to install that. I think it will take some time, but let's see. Yeah, in the meantime, maybe we can just set up everything. So instead of cartographer, maybe we can put it as Carto. Seems like that is installed. Carto is installed, so maybe we can start doing it. Yes, so the simulation start running, and maybe we can start the TF, but it's actually required for G mapping. But let's see for Carto. I think for Carto also it may be required. and I'm starting the Kato slam. Okay, so seems like it doesn't require that yeah, let me start the Kato. Yeah, it started, and you can able to see, right, the map is actually building. And if you use the RQT plugin to steer, I'm just closing, taking the steering plugin. I think I started the runtime. Yeah, steering plugin. Okay. So there is a question. Is there any way to cross verify what slam is running? Yeah, I mean it's not very difficult. I think by simply checking the ROS node list, you can simply find slam Kato. I mean the node from the node name, basically. Okay. Um like you can understand at least what is actually currently running. Okay. So here is some default setting for the Kato slam, and you can find it's actually like perform somewhat better than G mapping. It can be used for bigger area. Yeah, you can find. It's again a 2D slam. So yeah, there was cartographer, but we need to set that packages from source code, and there was no active development happening in that, but I will check it anyway, maybe in the next class. So here is how the Kato works. It's almost similar to the G mapping, but the advantage comes with the spacing. Like here you can find the spacing is actually like spacing in the sense the area, um, each grid corresponding to 1 meter. Okay, so the from the center it's like 2, almost 3 meter, so it's around 6 meter. Okay, maybe you can take this. If you take this 1 2 3 4 5, like 6 by 6. Okay, it's actually a floor of 6 by 6 meter, so which is not very big, right? So this kind of slam will be working good in small area. Okay, but if the area getting bigger, then there can be issues. But Carto, I think it will perform better than G mapping in a bigger area. Okay, yeah. So that is Kato, and maybe I can restart and we can check it for Hector. Hector is also we have installed. So let's see how Hector is performing. And then we can see the individual nodes after this. These all are demonstration. So we have seen how G mapping is working, and we can see the Kato and Hector next. Okay, so I'm just changing the name to Hector. Let's see how it goes. So I'm just saying the Hector, the advantage of Hector is that it will not take it will not take the odometry. So if you want to create a map of a environment without odometry, if your odometry is poor, then I think one of the algorithm that you can use is Hector. Hector is also using in drones because there is no odometry needed. It is basically working using the laser scan. Okay, you can see Hector. There can be issues in Hector, like if there is any issues in the robot. I mean, if the robot is not moving or something, then there can be issues. Otherwise, it's basically using the laser scan to create the estimate of the environment and create the map. So in a single run, I think all the SLAM algorithm that we have tested is working in the, I mean, it's almost working the same way, right? There is no much difference that we have seen. And yeah, so we have tried with Hector and Carto. Is there anything left? I think that's it, right? The cartographer is there. Maybe we can simply see the cartographer package. Cartographer ROS Neutic. So let's see whether we can set it up. I think it will take some time, but let's see. This is a repository, and yeah, there is only, okay, so this is a main repo, and let me see whether, okay, so we actually want the ROS cartographer, which is actually the wrapper. Yeah, it's not very actively maintaining now. Yeah, this is the I think these are the instructions, but there are much things to do. Okay, anyway, we can able to compile it now, but I think it's not very easy compared to the other SLAM. Okay, so they have tested in melodic, so it will be working in Noetic. Okay, it will be working in Noetic. So you have to follow this instruction. Basically, you have to fetch a set of packages from Git, and then we have to build it. Okay, so that is cartographer. Maybe we can actually see some videos of cartographer, so you will get an idea, which is actually performing much better than SLAM in some scenario. So this is one demo video from their website. Yeah, you can find it's the mapping is actually different. The logic of the mapping is, I mean, the algorithm is actually very different. It's pretty new actually. So you can find yeah, the mapping is very fast as well. Okay, and in order to test the cartographer algorithm, they already given some existing demo I mean back files. So using this back file, you can simply download it, play it, and then run the cartographer nodes, so that that will be like creating the map. Okay, so I'm just sharing that link as well. So there is a cartographer 2D and 3D. Okay, so there is a question, what is the purple lines on the map? Let me check. Yeah, it seems like okay, just a second, even I didn't observe. It seems like the trajectory, okay, it's a goal position, I think. No, it's not the goal position. There is no goal position anyway, it's a mapping, right? So okay, seems like it's an exploratory algorithm. Yeah, that's it. So these backfile, no, this backfile actually recorded, I think, not using manual joystick control. It's actually recorded using exploratory algorithm. So what happening is that just start the robot, start the exploratory algorithms, then it will be autonomously move around the environment and create the map. So you can see this sphere, right? These spheres seems like the goal position. Okay, so the robot will move to this goal position, and then it will get another random position, and then it will go to that position, and maybe it is keep on getting the goal position I think that is the, yeah, I think that is the either exploratory or they are giving a random goal position. So this demo, we can see they have set up the ROS navigation stack and the cartographer and maybe some exploratory algorithms. Okay, yeah. So that is the purple lines. I mean, these lines indicate it's basically the but it's actually staying that yeah, it may be in the exploratory algorithm. Yeah. Yes. So I think you have seen that demos of each one, and I think um, next will be, I think we can explain one by one. Maybe next class we can do that. Maybe I can also show you the cartographer 3D demo. Um, I didn't try the 3D yet, but seems like it is using the 3D point cloud and creating the 3D map. Okay, so we can configure cartographer as 2D and 3D slam. Okay, so maybe in the next class, in today's session we have seen some demonstration of algorithms, right? So maybe in the next class we can see from cartographer what are the input and output to the cartographer. We can quickly go through it, and also the hector slam and carto slam. Okay, we can quickly go through, and we can also talk about the rtab slam, which is a visual slam algorithm. I have worked with rtab before, so rtab and also maybe the HDL graph slam or something we can see with the 3D slam. There are many 3D slam algorithms available, so we can see this as well. Okay, so I'm not extending to 10:30 because my voice is still having problem, and I'm feeling like not very good with the sound, so that's why I'm not extending. So maybe in the next class we can start discussing on each we can take each slam algorithm and we can see the input and output of it. Okay, so that is what we are going to do next. After that we can conclude this session and maybe jump into controllers or some interesting maybe to legged robots or something. So I'm actually trying to cover interesting I mean topics first, then we can go to the other topics. Okay, yes, so that's it guys. So it's a time for questions. So you can ask if you have any question regarding the slam algorithm that we have um discussed today. So let me know if you have any question guys. So you can either comment or you can simply ask. Okay, so there is a question from Tejas. So we will go back to the topics what we have shifted from, right? Yeah. So we will be like, we have seen the demonstration of each slam algorithm, right? So now we will go back to the topics like what is the cartographer, then I mean an abstract idea of it, and input and output. Today we only like we have discussed about G mapping only and its demonstration, but we have some more slams left, so we will be seeing that maybe in the next class. It actually requires some time, so that's why today maybe I'm not sure. Yeah. Yeah, so again, the project, yeah, so that is again, we have to start the project, but because of my, I mean, it's actually due from my side. It has been a long time, so maybe what I'm planning is that it's actually in my task list, so I'm planning to like at least work for 10 tasks 10 projects. So I can't able to do that because of various factors. But I think this week I have to come back with that, because we we already have to start working on the projects, because of the one thing is that some members are coming up with their idea. That is fine. That is, I am actually welcoming that, because that so you don't need to wait for my list. If you want to get a list from my side, I think, obviously, I think this week, I think I will get time for that. So uh, yeah. So yeah, there is another comment. Yeah. Yeah, so we will be like, in the syllabus we will be like going with the some interesting topic, and then we will be like going back. Okay, going back, like, if we are not covering any other topic, if we missed anything, if it is important, then we will be like covering. Yeah. So Kalpesh is having a question. I'm interested in doing robot perception and navigation. Yeah, so there are a lot of interesting projects that we can do with this combination, or only perception. Okay, I am also interested in this area. So yeah, so you can also think about some idea, guys. You can actually, maybe we have a group called idea channel. Maybe I can introduce that. So this is actually the idea channel. So for the first batch, what I did was, I actually, I mean, asked them to come back with different ideas or innovative concept. Then, if that is, I mean, interesting, or if it is making value, then we can go with that, something like that. So one idea is like, you guys can also like just discuss the ideas in this channel, so I can also involve. So it's like a, I mean, group effort. We can get back with a interesting project idea. So if you have any idea, you can simply share it, and then others can also like take it, or they can implement. I can also contribute, but because of my time limitation, I can't able to like, I mean, invest much time on it. But I think this week I will get. The main reason was like, before 2 months I actually taken a project, and it's actually having, I mean, the commitment is actually very high. uh, so that's why I want to like, um, do, I mean, complete the course actually. For completing the course also we need time, right? So I am, and in the meantime I have some health issues, not I mean, not that complicated, but something related to the sound. Yeah, so these all are coming. So maybe you guys can contribute, and maybe next week I think I can also um, come up with some ideas. Yeah, so Rohan is having a question. Yeah, you can organize talk of former RDLP student, their experience. Yeah, so that's also we can plan. So we have a lot of people in connection. So their time also a problem. Like they are also working in different companies. So let me ask, okay, because one of the candidate who done a lot of project was France Butcher. There was, I mean, 3 4 candidate, they have done extremely well in the course. So this guy actually, he's working on some other technology, but he actually learned ROS as a hobby. Okay, so he created a lot of projects, and yeah, so maybe a session from France, or some advice from him, maybe good for you as well. So this was the main project he have done. It's a differential drive robot, and you can see it is having like a good number of stars and folks. So a lot of people are contributing to it. So yeah, so for them, my concept was to come up with, I mean, their own idea, But you can also try that, but I can come up with my own concept as well. Okay. Yeah, so Rohan is having a question. Can you recap what you skipped or remaining? Yeah. Um, so the thing is, like, we have skipped the chapters basically, like mostly the chapters. It's not skipping. Like I was just maybe someday I have some interest in slam, so I will take the slam. But someday it will be path planner, so that's why I'm just switching the chapters. So I know which chapters are remaining. I mean, we can check the content as well, right? So uh, based on the content, it's already there, so we can filter out which are remaining. Okay. Yeah, so regarding that, we can cover, no problem with that. Yes, yes. Is there any other questions? Yeah, this is rows 2. Okay. Fine. Yeah, so okay, okay. So there is yeah, for the recap, I think, I mean, the topics that we have discussed is already in the GitHub, right? So from that itself, we will get an idea what are the topics that we have covered and what are the things we have missed. So currently we are discussing not in the sequential way. We are taking some interesting topic and we are discussing, completing it, something like that. Okay. Um, so Tejas is having a question. So what is the project you are working on, sir, if you don't mind? Yeah, so I can share an abstract. So it is in ROS 2 Humble. So the project is basically like labeling on some it's an industrial automation project based on ROS 2. Basically labeling on each objects, some information we have to automatically label. So the task, it's actually, I mean, the client actually requires that they have um, I mean, lot of what application using this robot. So it's a combination of different robots, industrial robots basically, and we have to like innovate lot of things basically in industrial robotics domain. ROS 2 industrial, there is no ROS 2 industrial stack, so we have to work on a lot of things from our own. So we have to work with either CAT, then PLCs, all this stuff. So everything we have to write it from scratch. Okay. So some modules are available. Maybe we have to reuse. And also I'm working on some other projects. I mean, two projects are in industrial automation, and there are some side projects. I mean, that is not, I'm not giving much time, like the disinfection robots, then restaurant delivery robot, something like that. Okay, so these all are the side projects. I'm just mentoring them. Okay, yeah. And yeah, Rohan is having a question. We are not going according to the flow in the syllabus PDF. That's why. That's why, Rohan, I mentioned. We are not going in a sequential order. We are just uh, like taking some of the interesting topic and then we are discussing it. But all these topics will be in the GitHub, right? So based on that, we can easily find out which is missing. So I have an idea anyway. Yeah. Okay, okay. So I think we can conclude for today's session. So next session I will announce, and then we can complete the slam, and then let me see. I can start with rows and legged robots, which is interesting. Yeah, yeah. So so I have two things pending. One is obviously the project, and next is the session, next session. So maybe next session we can complete the slam, and then uh, the second session will be, maybe we can start with ROS and elect robot. Yeah. So basically, yeah, so I have because of the climate change and all, there is a problem. So hope I can fix that soon. Okay. Okay, everyone. Thanks for joining the session. So I will be sharing the video soon. Okay. Good night. So see you in next class. Bye, everyone.